January 2013. In South Korea, at the Woongjin polysilicon plant specializing in polysilicon production, there was a leak of hydrochloric acid from one of the 200-ton tanks. 760 people were evacuated. February 2017. In the German city of Oberhausen, there was a sulfuric acid leak at a chemical plant. As a result, a toxic cloud formed. This incident halted ship and train movements and prompted a partial evacuation. Over 150 people sought medical assistance due to respiratory issues. February 2023. In the state of Arizona near Tucson, a truck carrying nitric acid crashed. Authorities had to evacuate people in the area and shut down the busy highway. Such incidents are not uncommon, and every time they pose a great danger and instill extreme panic. Indeed, acids can be harmful, and you'd better know what they can do, so you could stay safe. But do you know everything about these substances that you probably should? Most likely the answer is no, and today you'll discover why are some acids strong and others weak? Why do we cry when cutting onions, and what does acid have to do with it? Where on earth is an entire lake of sulfuric acid? Which acid is so strong that it can only exist in space? What are the world's strongest acids capable of? And was the Breaking Bad series accurate? The most dangerous acids. Please leave this video a thumbs up to show the YouTube algorithm that it's worth watching. Thank you for every like, we always appreciate your support. First, let's briefly explain why some acids are strong and others are weak. Chemists associate the strengths of acid with their ability to donate protons to a base. A base is a substance that acts as a sort of antagonist, the opposite of an acid. Keep in mind that this is a huge oversimplification done solely to maintain your interest, so you won't get bored within the first minutes of this video. Our chemist viewers, thank you for your understanding. So, the weaker an acid holds its proton, the less energy the base spends to detach this proton, and the stronger the acid is deemed to be. These proton detachments eventually result in the destruction of substances the acids interact with. There are various ways and scales to measure the strength of acids. One of the most commonly used indicators is the dissociation constant known as Ka. It's also referred to as the acid constant. However, more frequently the value of pKa, which is an indicator of the dissociation constant, is used. The lower the pKa value, and please note the lower and not the higher, the stronger the acid. We'll be referencing this measure throughout our video. So let's dig right in. How can a layperson determine whether a particular acid is strong or weak? Of course, by comparing one acid with another. We'll start with the relatively weak acids and work our way up to the more potent ones. And the first on our list is uric acid. If you inferred from the name that this acid is somehow related to going number one, then you're on the right track. Our bodies are continually processing and eliminating metabolic waste, some of which is harmful or simply useless. In part, this is achieved through urine production and excretion. This process is called diuresis. The average diuresis of an adult ranges from 1 to 2 liters, 33 to 67 fluid ounces per day. And uric acid is always present in urine. However, its amount is very small. Its content in urine typically ranges from 250 to 750 milligrams. That's 0.009 to 0.026 fluid ounces. Moreover, this acid is very weak, with a pKa of 5.6. While this number might not mean much to you now, it would become a useful point of reference when comparing other acids later on. Though uric acid isn't potent enough to dissolve everything around it, it doesn't make it harmless. Like many acids, its effect can be quite insidious, especially if one has an improper and unbalanced diet. If the body fails to excrete uric acid, it accumulates over time, which isn't a good sign. An increased risk of heart attack or stroke and kidney diseases are among the most evident and likely consequences. In some cases, uric acid can crystallize, turning into microscopic needle-like structures that you can see here. They clearly resemble shattered glass. It's unsettling to even think that something like this can accumulate inside our bodies. These needle-like crystals can migrate throughout the body. When they end up in the joints, they can cause excruciating pain and swelling, resulting in gout. If they find their way to the kidneys, they can lead to further complications. As you can see, even a relatively weak acid can cause a lot of harm, and we're just starting to explore these substances. Now let's delve into an acid that everyone knows. Yes, it's your everyday culinary vinegar, which contains 4 to 6% of acetic acid. We should get to know this acid a little better, as very few people know some interesting facts about it. For instance, did you know that acetic acid is used extensively in perfumery? Giving vinegars distinct aroma, it might seem counterintuitive. You might wonder, how could it possibly be used in perfumes? In reality, acetic acid is widely used in perfumery and cosmetics as a regulator to create a balanced scent. So, despite its quite unpleasant, and pardon the tautology, acidic smell, this acid can balance out overly sweet fragrances. In its common store-bought concentration, acetic acid is an effective solvent. It's often used for cleaning various surfaces, especially when there's a need to eliminate an unpleasant odor. The higher the concentration, the more potent the acid becomes. 100% concentration is a very caustic substance that one should handle with utmost care. It's even recommended to avoid inhaling its vapors. Despite its seeming harmlessness and close association with food, concentrated acetic acid is a deadly poison. If consumed, just 20 milliliters, 0.67 fluid ounces of this substance would be enough to cause a horrifying and inevitable death. Initial symptoms will include a severe burn of the mucous membranes of the mouth, throat, esophagus, and stomach. This is followed by severe toxic effects such as compromised blood coagulation, resulting in extensive gastrointestinal bleeding. But impaired coagulation doesn't mean blood thinning. Quite the opposite. Victims would experience blood thickening due to plasma loss from the damaged mucous membranes, leading to shock. Additional complications include acute kidney failure and toxic liver dystrophy. And all this damage can be caused by just this small amount of acetic acid. At least it's almost impossible to accidentally swallow it because of its sharp smell we've mentioned previously. One can't simply confuse it with something. How about another acid commonly associated with healthy food that's even more dangerous and more insidious too, since it's completely odorless? This is oxalic acid. If you're a fan of a healthy diet, you might unknowingly consume this acid regularly in your food. It's found in many types of leafy greens. This acid is especially abundant in spinach, but is also found in sorrel, rhubarb, radish, mango, cranberry, pear, apple, and pomegranate. All of this sounds very benign, and you might think that it's completely harmless, but as you can guess, it all comes down to concentration. With a pKa value of 1.25, oxalic acid is significantly stronger than acetic acid, which has a pKa of 4.75. Its potency, combined with its odorlessness and several other properties, has made it very effective in various applications. The most popular uses for this substance are bleaching and cleaning. Oxalic acid helps to remove rust, which is why many bleaching or cleaning agents contain this chemical compound. It's also employed in water softening and purification, and is one of the ingredients in disinfectant cleaning products for sinks and toilets. In analytical chemistry, it serves as a reagent. Furthermore, beekeepers use a 3% solution of this substance to rid their bees of parasitic mites. It's starting to sound less and less appetizing, doesn't it? And for a good reason. In high concentrations, oxalic acid becomes just as deadly as acetic acid. A mere 15 to 30 grams equivalent to about a tablespoon of this substance can be fatal for an average adult if accidentally ingested. Remember when we talked about the sharp crystals formed by uric acid? Well, oxalic acid can crystallize the same way. Its primary killing power comes from the acute kidney failure due to the formation of solid calcium oxalate deposits in the kidneys. Even the fumes of oxalic acid are hazardous given how much they destroy the mucous membranes. While the three acids we've discussed can be quite hazardous and dangerous, they are far from the sheer horror sometimes depicted in the movies. We've all heard spine-chilling stories of villains dissolving their victims in acid. Whether this is true is up for debate, but the film industry certainly does justice to these stories. Everything we've discussed so far has been theory, but now it's time for practice. Almost all the experiments with acids that we're about to describe, we conducted ourselves in our ReYOUniverse laboratory. You'll get to see real footage, real substances, and real danger. And now we are going to learn about the acid that has gained real popularity all over the world thanks to the TV series Breaking Bad. It is it that was the favourite way of eliminating evidence of organic origin in the series. It is a very interesting chemical substance, quite controversial and surprising in some cases. You're about to find out why. In one episode of the series, the protagonists use hydrofluoric acid to conceal any traces of a crime. With just a few gallons of hydrofluoric acid, they managed to dissolve an impressive volume of pure organic matter, melt the bathtub and destroy the floor in just a few hours. But in real life, this is almost impossible to do because hydrofluoric acid is considered weak. And its dissociation constant pKa is 3.17, so it's not particularly stronger than acetic acid. But how is that possible? After all, it's well known to dissolve glass. And that's something almost no other acid can do. How can an acid with such superpowers be considered weak? Actually, the trick here lies in the selective action. The scriptwriters of Breaking Bad didn't completely deceive us, but they did embellish things a bit. Hydrofluoric acid is indeed regarded as weak, and the effect shown in the series can be achieved only by adding other chemicals. However, one should be very careful when working with this acid as it belongs to the second class of danger and its vapors to the first class. So, things are getting very confusing here. Why is it so dangerous if it's weak? It's all about the same selectivity of action, plus the relativity of the concept of weak acid itself. It is weak compared to superacids, which we will discuss a bit further. But it is rather aggressive in itself and is capable of dissolving and reacting with many substances. Diluted acid is especially insidious. When its splashes get on the skin, a person may not feel anything at all. Meanwhile, however, the substance will be quickly absorbed into the skin and will enter the bloodstream. In about a day, symptoms of toxic poisoning, pulmonary edema, cardiovascular and gastrointestinal disorders will appear. This will all happen because the compound will form insoluble calcium and magnesium salts. And after all, calcium and magnesium are vital elements for our body. Once in the bloodstream, even a small amount of hydrofluoric acid will bind these elements throughout the body, literally destroying it at all levels. That's how this seemingly weak acid can do a lot of damage. And for the aforementioned property of dissolving glass is an almost unique property. The point is that fluorine, which is a part of it, is a much stronger oxidizer than oxygen, and that's why it seems as if it could dissolve anything just as easily. But how is it really? What did the writers of Breaking Bad deceive us about? Let's get to the bottom of this. This acid reacts with most metals, forming salts, fluorides. But it can't dissolve lead, platinum, gold and palladium, regardless of the concentration.
Fluoroplastic, polyethylene and other plastics as well as wood are also resistant to its influence.
This is especially noteworthy against the background of what sulfuric acid can do to wood. You'll soon learn about that too. Hydrofluoric acid is able to scarcely oxidize and dissolve such a large piece of organic material as in the series in about 8 hours. However, complete dissolution still won't happen. But what do we see in that episode of Breaking Bad? Acid dissolved almost everything, and in addition, the bathtub and the floor in just a few hours. And that's pretty far from reality. To get at least a roughly similar effect as shown in the series, it would take not a couple of gallons of acid, but at least 100 litres, 25 gallons. And it would have to be mixed with a significant volume of a special additive, a catalyst that accelerates the reaction. Once the catalyst is added, the chemical reaction will instantly become very vigorous. It will release a large amount of heat and gas in the form of a huge cloud of vapor consisting of carbon dioxide and hydrogen. But the acid will not be able to dissolve the bathtub and floor. After the reaction is completed, only carbon, sulfur and black sludge will remain at the bottom. Of course, we'll not provide the recipe for this infernal mixture and will warn you once again against chemical experiments at home. And in order to vindicate this amazing chemical compound among law-abiding citizens, we shall say that hydrofluoric acid, of course, was not invented for such terrible things. In fact, it's used in many industries, including even in modern nanoelectronics in the production of processors, transistors, and other solid-state silicon devices. Hydrofluoric acid can be conventionally considered as a kind of medium in strength due to its selective action. But there is a class of acids that are explicitly called so strong. And one of the most vivid examples of this class is nitric acid, with a pKa index that is already negative, minus 1.64. Nitric acid dissolves all metals except for gold, tantalum, and metals of the platinum group. When acting with some other chemical elements, the acid decomposes into salts, nitrates, which dissolve well in water and are used as fertilizers. Only glass and Teflon do not react to nitric acid at all. But the ability to dissolve everything is not the only frightening property of nitric acid. Its insidiousness lies in its ability to create extremely explosive compounds when reacting with other substances. This often leads to accidents, sometimes very destructive. For example, in 2015, residents of Spanish Catalonia experienced great fear from a man-made accident at a chemical plant. The acid was accidentally mixed with ferric chloride, another dangerous compound. This grim mixture caused a powerful chemical explosion. Fortunately, no one was killed. Only 3 workers were injured. But the whole thing looked apocalyptic, if not infernal. A huge toxic cloud rose into the sky, because of which 65,000 residents in 5 cities could not leave their homes for some time. The cloud itself was of a horrible orange color, which further terrified the unfortunate residents of the plant's vicinity. But despite the danger, it would be very difficult for modern industry to do without nitric acid. The field of its application is very wide, from manufacture of explosives and rocket fuel to plastic production. It's also used to determine the purity of precious metals, and it's also actively used in medicine, in dentistry, for anesthesia, as well as for treatment of skin diseases, for example, for burning of warts. With all the impressive and terrifying properties of nitric acid, this is still only the beginning of the story because it's still far from the strongest in the range of strong acids. Hydrochloric acid is surely much better known, widespread, and literally close to everyone. From the school course of biology, we all know that it splashes in each of us in the stomach and provides the primary digestion of food. And it's much, much stronger than hydrofluoric acid. Its pKa is about -7. This negative value indicates a very high degree of acidity. So why doesn't it burn through the stomach walls? Another paradox? There are 2 reasons. First, the cells of the stomach produce very weak hydrochloric acid. Its content in gastric juice is 0.3 to 0.5%. But even this is enough for quite a powerful effect. Everyone has once experienced heartburn, and this torturous feeling can hardly be mistaken for something else. And secondly, the stomach walls can protect themselves. The surface is covered with neutral mucus, and the stomach cells are actively renewed. The hydrochloric acid in high concentrations is extremely dangerous. Exposure to it entails severe chemical burns of the skin, not to mention the mucous membranes. Its ingestion is almost certain death. But for mankind as a whole, hydrochloric acid is a loyal helper. It's used everywhere, in the chemical industry, mining, metallurgy, food industry, oil and gas production, and everywhere else. At this point, many might wonder, what happens if you mix these acids? Will it create an even more powerful, hellish concoction? Or will the acids neutralize each other? It gets even more interesting. By mixing nitric acid and hydrochloric acid in a 1:3 ratio, you get a substance with one of the most ominous and poetic names in all of chemistry, aqua regia, or royal water. Of course, it's not a drink. It's truly a hellish mixture, capable of things that neither acid can achieve alone. For example, it can dissolve gold and even platinum. It easily handles other metals too, and just for you, we've performed an experiment. Here we have a beaker with that very same. When freshly prepared, it's colorless, but it quickly takes on this hue. At first, the reaction is slow. Bubbles rise from the spoon like mild fizz in soda. But after 10 minutes, the acid turns a dark brown, becomes opaque, and bubbles vigorously. A few more minutes and the spoon collapses. Its lower half has been almost entirely eaten away by aqua regia. In under 30 minutes, the mixture completely destroyed a metal object. And here, finally, we are close to the most dangerous boundary in the gradation of strength and danger of acids. Because we're going to talk about sulfuric acid. You've certainly heard about it. But some of its properties will be quite surprising to you, and you're about to learn them. Let's start with the main point. Sulfuric acid is deadly and toxic. Yes, just like that, with no alternative. It is so powerful that its aqueous solution of 40% or more is already considered to be concentrated sulfuric acid. It even dissolves silver and palladium. It can't dissolve only gold and platinum. So what can it do to live in organics? Well, see for yourself. Let's lightly spray some slices of bread with acid and see what happens. At first, it seems like nothing's going on. But soon you can see the parts of the bread that came into contact with the acid darkening. And the reaction only intensifies. Here's what the bread looks like just after 5 minutes, and here after 10 more minutes. Something's clearly smoking, bubbling, and looking thoroughly unappetizing. The effect is much faster and more dramatic if you pour sulfuric acid onto a roll of toilet paper. It's made of pure cellulose, and sulfuric acid loves cellulose. In just seconds, the roll turns into a smoking, bubbling, coal-black mass. By the way, doing the same with sugar produces a similar result. The substance slowly transforming into a black, sticky, smoking sludge. Here again, we can't help but think of legends about villains dissolving their victims in baths of acid. But baths are not the most impressive thing. How about a whole lake of sulfuric acid? You say that could only happen on Venus, wouldn't you? And you'd be almost right, because our cosmic neighbor definitely has thick clouds of sulfuric acid. But it's still too hot to have lakes on its surface. What about Earth? Is that possible? It's absolutely possible. The places with volcanic activity will tell you the truth. This is Ijen. It's an active volcano in Indonesia. And here in its crater, Lake Kawah was formed. It's recognized by the Smithsonian Institute as the largest high-acid crater lake in the world. It has an acid-base pH of just 0.2. Is that high or low? For comparison, pure water has a pH of 7. And the electrolyte in lead batteries has a pH of 0. So it's not hard to guess that swimming in such a lake is a very bad idea. To be as objective as possible, let's say that the water in this lake cannot be called a solution of sulfuric acid. It has sulfate chloride composition with a lot of other impurities. But this is still the closest lake to one that could be called an acid lake, and moreover the largest on Earth. Would you like another frightening yet amusing fact about sulfuric acid? If you've ever sliced a fresh onion in your life, you know that you can shed a lot of tears in the process. Well, that burning in the eyes and the defense reaction in the form of tears is provoked by nothing other than sulfuric acid. That's what you can read in many sources, even very reputable ones. And there is a grave inaccuracy here. But don't be disappointed, this myth is not entirely a myth. Here's how it really is. The volatile oils that give onion its distinctive sharp flavor and odor contain a class of organic molecules called amino acid sulfoxides.
When an onion is sliced, enzymes, alliinases, are released that convert these molecules into sulfenic acids. These, in turn, spontaneously restructure to form syn-propanatyl X oxide.
It is this chemical that irritates the eye mucosa, causing tears. Note, sulfenic acids are not the same thing as sulfuric acid, although the names are very similar. The play on words with the root sulf, referring to the Latin name for sulfur, misleads many people. And that's where this myth about sulfuric acid in the eye comes from. But let's get back to the real sulfuric acid because it can give us even more surprises. For example, it can be strengthened many times, and it's very easy to do. You'd think, what so special can happen if a well-known and relatively safe substance, hydrogen peroxide, is added to sulfuric acid? But in fact, this mixture is so harsh that it even has a creepy nickname, piranha. And this nickname fully describes the properties of the substance. It dissolves almost any organic matter in minutes or even seconds. And not only that. Let's run another experiment and give this powerful acid a more difficult challenge. Let's see if it can dissolve a living flower. We place a rose into a flask, carefully pour in piranha solution, and at first, it seems like nothing is happening. But after just a couple of minutes, you can see a layer of dark brown sludge forming beneath the flower. Gradually, the entire flower dissolves before your eyes. In fact, it was created specifically for this purpose, to dissolve organics at lightning speed. But why? One can't help remembering the myths of dissolving bodies in acid baths. No, it's much more prosaic than that. This solution was created for absolutely peaceful purposes. The action of this liquid piranha is narrowly focused. It copes best with organics, but spares many other substances. That's why it's widely used, for example, in microelectronics for cleaning silicon plates. Let's move on. It's not for nothing that we said earlier that sulfuric acid is a dangerous frontier. The reason is that it is a kind of standard and a starting point for further classification of strong acids. To be more precise, the class of strong acids ends with sulfuric acid and then begins something much more terrible in its destructive power. Superacids. And believe me, they can do such things that even scientists unwittingly assigned almost magical properties to some of them. The term superacid was proposed by the famous chemist James Bryant Conant back in the early 20th century. The scientist's motive is easy to understand. It's somehow hard to use the same word, acid, for substances that are incomparably more powerful than all inorganic acids known at that time. Moreover, these substances turned out to be so different and peculiar that soon a separate field of chemistry was formed, the chemistry of superacids. Superacids are obtained from two or more different strong acids, but there are exceptions among simple compounds. The closest example is perchloric acid. It's not technically a superacid in the full sense of the word, but it is much more powerful than sulfuric acid. Its pKa is -15.2. For comparison, sulfuric acid has a pKa of only -3. It's not hard to guess that it's capable of even more frightening things. But still, if you're not a chemist, some of its properties will be an amazing discovery for you. In addition to its ability to dissolve, perchloric acid has another destructive property in its arsenal. It is extremely unstable, and when mixed with other substances, it becomes explosive. On February 20th, 1947, a massive explosion at the O'Connor Plating Works in Los Angeles took the lives of 17 people and injured more than 100. 11 nearby buildings were damaged beyond recognition. Press reports stated a 25-foot, 7.6-meter crater. And the cause of the tragedy was simply the mishandling of this devious acid. At that time, the facility was trying to use it for an experimental method of polishing aluminium. On the day of the emergency, the refrigeration unit needed to safely store the perchloric acid had malfunctioned. The 490-litre, 130-gallon tank of acid boiled, which increased its instability many times over. The slightest external impact was enough for detonation. And it happened. A plastic rack was lowered into the bathtub, which caused a huge explosion with such terrible consequences. And now we'll get acquainted with a real superacid, which is classified as such without any conventions. Not only that, but scientists have called it magic for some of its amazing properties. This is one of the most famous superacids. It's obtained by mixing fluorosulfuric acid and antimony pentafluoride. It was first obtained in 1966 in the laboratory of George Euler, Case Western Reserve University in Ohio. It received its fancy name after one of the lab's employees dissolved a holiday candle in it at a New Year's Eve party. The NMR spectrum of the resulting solution showed the presence of a pure tert-butyl cation. You didn't get anything. Neither did we. You have to be a chemist to be impressed by a paraffin candle being dissolved in acid. But back then, chemists weren't simply impressed, they were almost shocked. So we'll just have to trust the impressionable scientists. This is why this class of acids has earned the reputation of being magical. Magic acid was by no means just a laboratory fad. It has found practical applications. For example, it's widely used to break down low-quality gasoline into carbocations so that they can create more complex bonds and produce higher quality gasoline. That in turn is used in racing cars. So we've already reached the magic, albeit in a figurative sense. But what can be cooler than magic? Only chemistry. Because there is something that is much stronger than even magic acid. It's fluoroantimonic acid. It was once considered the strongest acid in the world. Recently, it had to give way to a new favorite which we'll soon discover. So fluoroantimonic acid is an absolutely insane powerful mixture that can do more than just dissolve the skin and flesh of a living creature. It can also dissolve bones and then almost any container in which it's stored. It is so aggressive that it's even theoretically difficult to identify media and materials with which it would not react. The only thing it will spare is Teflon and other types of fluorinated plastic. And that only for the reason that they are its distant relatives. After all, the chemical name for Teflon is polytetrafluoroethene. The key word in this unpronounceable word is fluorine. That's what makes these substances relatives. Carborane acid is the strongest acid in the world. Well, you'd think it couldn't get any stronger. It would seem impossible to create an acid that would be stronger than this terrible monster. But the nature and science never stop surprising. Here we are, carborane acid. This is the strongest acid that can be produced and stored in a laboratory. It's about 1 million times stronger than concentrated sulfuric acid. It's so strong that scientists can't measure its power using conventional scales. That's because it protonates all known weak bases and all solvents in which it dissolves. It was obtained by a group of scientists from the Department of Chemistry at the American University of California under the guidance of Professor Christopher Reed, together with colleagues from the Institute of Catalysis, Siberian branch of the Russian Academy of Sciences in Russia. It is, moreover, a very complex chemical compound. Actually, it was called carborane for you and me, ordinary people. And if you want to feel like a scientist, try to pronounce its full name according to the nomenclature of the International Union of Pure and Applied Chemistry. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Undecachloro 1-carbocloso-do-decaparborane. Now here's a surprise. Even this superacid has a stronger modification, fluorinated carborane acid. Its formula is almost the same, but instead of chlorine, its molecule contains fluorine. That's what is currently the queen of acids. Nothing on our planet is stronger than it. Postscriptum.
You thought that was the end of it, but we said on our planet, and that changes things. Indeed, fluorinated carborane acid is the last superacid that can be somehow stored. But there's something that is also an acid in chemical terms and yet is not possible to store it. And that's just the least of its amazing properties. What's this substance? It's helium hydride ion. It was first obtained in the laboratory in 1925, and the fact of obtaining it was recognized only by the indirect signs. The ion is stable only in complete isolation. This substance can't be prepared in any volume. That's because it will react with any, let's emphasize any, other molecule it is exposed to. Scientists have been speculating about its existence in nature since the late 1970s. But in nature doesn't mean our planet. It's simply not possible at all. It was thought to exist in space, and not just in space, but in the interstellar medium, where it would encounter nothing it could react with. And indeed, the helium hydride ion was finally detected in April of 2019 using the Sophia Stratospheric Observatory. And it was discovered in the NGC 7027 nebula, which scientists proudly report in the Nature journal. Scientists believe this is the very first chemical compound to be formed in the universe, and it is fundamental for understanding the chemistry of the early universe. That's it for sure now.